Hi, I'm Tony.
And I'm Patrick.
We want to welcome you to another discussion from Ch.8 to the Cross Apologetics, and we're working our way through How to Be an Atheist by Mitch Stokes, and we have gotten to the 8th chapter where he talks about, he's in the section on science.
Right.
And this is he says, the current crisis. So last time we talked about this issue of realism and instrumentalism in science and how they worked, and he suggested that from an instrumentalist perspective, in fact, he says, in the last chapter, we consider reasons to think that science might not tell, he tells us, the sober truth about the world beyond observation. So that would be an instrumentalist perspective, right? Instrumentalist says, we don't care about the truth just as long as the theory works, right? That's the kind of
They're the opposite of Tom Cruise and the courtroom scene.
Yeah.
I want what works.
Yeah.
That's the Jack Nicholson approach.
That's right. So so we now have come to an issue that he wants to talk to us about with regard to physics. Right?
Yeah, this one he titles the current crisis, but I think we've been in crisis as far as the public kind of perception of what science is. It's not that bleak of a plug and chug your numbers that we went over in the past couple chapters. But here we're going to take a look at kind of our reigning theories of the day, and we start with a look back at, well, what about the past theories? Was it just, the scientists of the day kind of went along and used what they could, but really knew that they didn't really have all the answers? Well, no. In fact, the history of it, at least where he starts with Newton, and so he provides this overview that says, for pretty much 2,000 years, science was done with this kind of Aristotelian model of things go up because that's the way that they were designed to, and things go down because that's their nature. Yeah, that's their nature. Yeah. That's something that's within itself that directs. And Newton comes along with his fancy calculus, or Leibniz, or really probably both of them at the same time. And
although I think Newton won, at least we give Newton the victory.
I mean, right? He's the Sir and the Sir Isaac Newton there. But he comes along and gives meaning to the chaotic behavior of physical objects in uncanny detail. So here comes Newton, and I mean, he had backings. In fact, his knighting is even a political maneuver by the Queen at the time to kind of curry favor. So his benefits for science is, I mean, huge. You can't touch on the history of thought, philosophy, science, really anything without acknowledging what Newton did as far as a revolution. Yeah,
part of the importance of it is how he attached mathematics to it, right?
Right. Yeah, and we kind of same thing with Galileo. It seems, looking back on it, we go, oh well, all you had to do was drop an orange and a grape and go, well, they both fall at the same speed. Why wouldn't you just do that? Well, no, it's there's always kind of those defeaters that we talked about where you just it was the wind, or you drop the hammer and the bowling ball, and well, of course the bowling ball is going to hit because of the wind, but if we were able to do it on the moon, and then when we were able to go to the moon, we proved that Galileo was even right back then. So
that they fall at the same rate.
Right, exactly. Yeah. Yes, even at 1/6 the gravity. So during the 16th, 7th century, scientists even applied his physics, so much so that they thought it was the answer for almost everything, including things that aren't physical, that are physics, which are chemistry and biology. They really tried to factor in this mathematical approach, this new scientific approach that kind of Newton popularized, came up with, and turned about. So much so that Lord Kelvin, from 0 degrees Kelvin, which freezes all matter in the universe, announced that physics was complete.
How about
Look at that?
Yeah,
we
Newton
didn't have to
did
do
it. Right?
Any more work.
Yeah, Newton's deal was he was the end all and be all of physics. Right.
They were coming up with things. They were finding real answers, and real answers that were true. That it wasn't an approximation as far as they were. It worked. In fact, Newtonian mechanics is still taught, and we still think in Newtonian ways because of just how great it is. I mean, you really don't get into quantum mechanics and general relativity unless you're taking kind of third level physics in college. So, I mean, you even do Newtonian mechanics in college as well until they pull the rug out from underneath you until it's a different story. So Lord Kelvin here says, we pretty much got everything handled except for these, what he calls dark clouds on the horizon, things that, kind of muddled, but we'll get there. We'll eventually get there. We just need to, hone the math or come up with new technology. And so there again, what we talked about before is scientists have this really difficult approach of defeating their theories. They don't say, well, here are a few places where Newtonian mechanics seems to
be strained.
It's hard. They really couch it in that kind of,
but they don't give up the theory, right?
Right. They don't say, well, it's good enough for now, but we definitely know it's not true. Especially because instrumentalism, it kind of comes at a later time, or at least has a wider acceptance at a later time. And so with this dark clouds on the horizon, it turned out to be exactly where quantum theory and relativity comes in and pretty much takes the knees out from underneath Newton and Einstein and the people that came up with quantum theory kind of reign for a while, as of right now. So that's what we're going to be looking at. Is we're going to be explaining to you through Mitch Stokes anything to do with quantum theory or relativity.
Yeah. So he says, although Newtonian mechanics is an excellent approximation for medium-sized dry goods at velocities far below the speed of light, when we address the most fundamental aspects of physical reality, when the universe redlines, he tells us, physics becomes an extreme sport, and we need quantum mechanics and general relativity. Right. So Newton does. I'm sorry, Lord Calvin, right? You were wrong. Newton was not the be-all and end-all, right? In fact, we progressed beyond Newton in the early part of the latter part of the 19th and early part of the 20th century, where quantum mechanics and general relativity were developed. He says both of these, though, they need one another. Neither of them, notice this, neither of them can account for physical reality alone. Right? So neither quantum mechanics nor general relativity can work on their own. So quantum mechanics talks about the very small, right? General relativity talks about the large, and the very large, and even medium sized. Newton is okay for medium sized stuff, right? But when you get beyond that, or you get way, or in terms of very large, like black holes and all that kind of stuff,
Stars,
and you get below that in terms of these quantum particles, Newtonian physics fails us, and so we have these two theories now
that work for different aspects
of reality, right? But the problem is, and he calls this section in the book a strained relationship, right?
So again, look back at what Calvin is saying, what Newton probably understood is, hey, he was a little bit probably on the spectrum, but he probably thought, I finally cracked this code with this calculus deal, and so this dark clouds thing, it's there, but we're kind of treating it as we'll eventually get there. We're in the early stages. We're now in that period of we got it figured out. Look, we've got the atom bomb, we got the computer chip. We're able to photograph with mathematical certainty a black hole. We're able to test the bending of light in gravity. This is amazing. But here, as you're saying, the two are diametrically opposed to each other, but we kind of consider it as science. It's true. It works. It's the truth. We've got there. It's just we kind of got to work out the middle. So it's the opposite of what Newton is. So maybe the next one will factor in all three.
So he tells us our two pillars, that is quantum mechanics and general relativity, are logically incompatible. right, with one another. And so at least if that's the case, then at least one of them has to be wrong, right? I mean, if they're logically, they tell us different stories, he says, about the unobservable world, right? So, although, they both work within their domains, they don't work when you try to apply one in the domain of the other.
Right.
And so we know that one, either they're both, wrong, or at least one of them is wrong, and we have to figure out a way to make these things work together, right? So he says, but he tells us few outsiders have heard of the irreconcilable differences between general relativity and quantum mechanics. And then he quotes Brian Greene here. He says, in all but the most extreme situations, physicists study things that are either small and light, like atoms and their constituents, or things that are huge and heavy, like stars and galaxies, but not both, right? This means that they need use only quantum mechanics or only general relativity, and can, with a figurative or flirtive rather glance, shrug off the barking admonition of the other, right? So I'm focusing on quantum mechanics, you're focusing on general relativity, and they work in the areas that we're trying to focus on, right? Either quantum mechanics with its very small atoms and all of those little subatomic particles and that sort of thing, or the very huge and heavy stars and galaxies that we work general relativity in. But and so mine works, right, and yours works, but not together.
Right. And for 400 years, we've been teaching elementary to college-age students the middle, and so everyone's able to do that old Newtonian mechanics, and so the medium kind of gets lost in it because everybody can do that. So that's not the cutting edge of science. You have to be able to come up with weird equations with letters instead of numbers.
So he tells us that physics needs a theory that can combine or unify these disparate phenomena. For example, there are physical situations where physicists would really like to use both theories simultaneously, right? But they're not able to, right? For instance, for extreme physical situations that are both massive and tiny. Well, you need to use both of the theories in those types of situations, but we're not able to because the two theories are incompatible, right? So when the mass of a star, for instance, or a universe is packed into a volume smaller than an atom, we have to take gravity into account along with quantum effects. So there again is an example where we need both of them, and we're unable to do it. Right? We might say a quantum gravity theory that we don't have. Right. So the idea here is we need a unified theory. That's the search right now that we're going through. And we don't have a unified theory, and so physics, as a result of that, is incomplete. Right? It's incomplete.
It's this thing where on two sides of the equals, you could get a zero, but there's some missing variable there that scientists are just sure is there because, look, you have the x equals quantum mechanics, and that works for that side of the equation, and y works on that side of the equation for the small things for quantum, and so that scientists have this attempt to say, well, there's probably something that combines these together because they work, but as we saw with Newtonian mechanics, sometimes it's just all wrong, and you have to come up with different theories. So here's their attempt, still, which we are in the process of, as far as 2019 is concerned. If you're from the future and you're looking back at how primitive we were, it's true because and this is the point, is we need to be intellectually honest with what science says and does, and so this is what scientists are attempting to do with kind of building this unified between the two, so unifying both theories.
Exactly. So they've come up with several theories here, or at least a couple of ways to do this, right?
Yeah. String theory.
Yeah.
String theory, which makes very much sense that we're going to not read directly from the book, but this is the thing. So one of these theories is probably you've seen on the Big Bang Theory or Fringe, or pick your gobbledygook Star Trek, where you can just say the word string theory and quantum fields and zeta reticuli particles, and you just go, yeah, that sounds like sciencey words. The string theory is an attempt to develop this unified field of unified theory of gravity, and you have it also called superstring theory, and it's pretty much been started since 1984. It's radically changed our views about the fundamentals of reality, so much so that we no longer consider elementary the particles like electrons, quarks, and bosons and all that stuff. We don't consider them elementary or fundamental. Instead, they're composed of these strings. They're not just a single point. They go somewhere into this string type thing, and the scientists who know these things are able to do things with them and come up with mathematical equations that seem to try and get to the truth, or a working truth, probably. Yeah. So according to superstring theory...
So these particles are made up of strings.
Yeah.
That's the idea, right?
Yeah.
So
every particle is composed of tiny filament of energy, some 100 billion times smaller than a single atomic nucleus.
Wow. So that's... You can't...
that's so small. Yeah. You're going to have to come up with a different version of the electron microscope, because it's even more than that. And its shape is a string. So think of it like a violin string that you can pluck, and it vibrates in different patterns. Each will produce a musical tone, and we even see that in the medium size. So these vibrations, though they don't produce musical notes, the theory claims that they produce different particle properties. The negative charge, the positive charge is there, whatever the quarks are supposed to do. All those have their kind of basic building blocks within this string. So it's that kind of Zeno's paradox, where at what point do you divide until you're at infinity or zero, and you're just never going to get there. So it seems what it's going to be doing. So string theory attempts to unify all these particles into a single kind, and it's extremely attractive. Why? Because it explains why particles like electrons, quarks, leptons have characteristics that they have. Whether or not that's true, we don't know, but hey, it attempts to explain why, which is interesting, because the why seems to fall back into our philosophy theory. Why do things rather than what do they do?
Right.
So this is kind of stomping on hollow ground of old. So it accounts for all four forces, things like, let's say I had the four. Gravity is one. And
electromagnetism, strong and weak.
Yeah, there you go. Yeah. Nuclear forces. So it attempts to unify all physics. So the big, the small, and then everywhere in between kind of gets brought along into those. Our universe is actually composed of 9 spatial dimensions along with a single time dimension. Our universe has 10 dimensions instead of 4.
So this is according to strings.
Right, according to strings. So if you think of what our current theory is the 3, length, width, height, the point, and then time from Einstein using it. And
so now we get 10 dimensions.
Yeah,
right?
at the very least. I always joke about 222 because that's one of the outlandish theories, because how do you imagine 222? And there's a really good book by Edwin Abbott, who is so good he has to repeat his last name twice, called Flat World. That is really good because it talks about, imagine that you're a shape that's on a 2-dimensional plane. What would interacting with a third-dimensional object within your world attempt to look like? So, you have the pyramid come down into the flat world, and it starts off as a point and then gets to a line and then a bigger line and a bigger line and a bigger line until it finally takes up the entirety of your horizon and then disappears. Well, what was that? Well, it was a point and then a line. That's amazing. But from a third-dimensional point of view, it's a pyramid interacting with a flat plane. So that's a really good book that that kind of says, okay, well, why should we take 9 dimensions as, able to be thought of? Well, it's because you exist within the 3 dimensions that you experience. And so how do you get outside that? And so for people who kind of scoff it off like I do, there's always that book that makes you go, okay.
He does make the point here that string theory is really almost kind of a throwback with regard to Pythagoras, the Greeks, the early Greeks, Pythagoreans, right? Who also argued that math was kind of the basic idea of nature, and they got that from musical notes, right? So these strings, right, that each of the various musical notes.
When we see that with octaves and fifths and fourth and whatever Einstein as a hobby played the violin, and there's probably a good story within that to harken back to Pythagoras and his point.
So we've come full circle.
Yeah,
right?
full
Back
string circle.
To Pythagorean theory. Right, and of course, the mother of all string theories, he tells us, is M theory, right? He says, as it turns out, though, there are 5 different kinds of string theories, each with characteristics working in respective domains. One of the contributors of string theory says that for a theory that makes the claim of providing a unified framework for all physical laws, it is the supreme irony that the theory itself appears so disunified, right? He says the theory itself is not unified. To someone learning the theory for the first time, it is often a frustrating collection of folklore, rules of thumb, and intuition. And at times, there seems to be no rhyme or reason for many of the conventions of the model. So string theory itself may not be the final theory we're looking for, right? And so what we come up with then is a second string theory revolution. So the first one was in 1984. This one happened, he tells us, in 1995. And, a second superstring theory revolution. And it was called M theory, right? So he says we met M theory when Hawkins and his co-author employed it in their argument for a universal universe that spawned from nothing. M theory, recall, is the unified theory Einstein was hoping to find, the one that will, after 3,000 years, show us the grand design, right? And so M theory is a network of theories in which each theory is good at describing phenomena within certain range. So that's the basic idea of M theory, right?
In other words, need multiple M theories. So MM theories and within multiple universes. So MMMM theory. So it's just the M and M theory.
Yeah. So M theory requires additional spatial dimensions over the individual string theories, bringing the total dimensions now to 11. So we've popped up another dimension here, right? So we're recreating dimensions with these theories. The problem, though, he tells us, is not enough evidence, right? He says, but there are very serious problems with all forms of string theory, including M theory. A particularly troublesome one is that there isn't any, notice, empirical evidence for them, nor perhaps can there be. Yeah. So there's no evidence for these, right? There's no way for us to make any empirical. In other words, and this is, they're unobservable. And they are more than unobservable. We can't even observe what the implications that they give us, right? So this is a problem. This is a pretty dismal situation for empiricism, right? He says one of the problems related to this lack of empirical support is that there are a lot of individual string theories within the 5 classes of string theories, as many as 10 to the, you ready, 500th power, right? And this is one of those cases where more isn't better, right?
Yeah, it's like golf score. You want to get to 1.
So string theories that we know how to study are known to be wrong. That's the problem. And those that we cannot study are thought to exist in such a vast numbers that no conceivable experiment could ever disagree with them all. So the ones that we know of are wrong. The ones that we can't that we don't know of or that we think are, we can't have any experience or experiment rather to show whether or not they're wrong.
Right. This isn't like games of free cell where it's you just got to figure out the right collection of cards and each game can be won. 10 to the 500th power is 10 or 1 with 500 zeros next to it. Yeah. That's a large number, so much so that Google wouldn't even name its next search engine after it. But you have this kind of reverse idea that science has kind of come up with on the back end, where again what we looked at is this instrumentalism, saying, well, we don't know if it's true, we don't care that it's true, but it works. And so you can almost say at least that's your starting point, as far as if you want to be a good scientist, if you want to have a good understanding of science, at the very least it should work. But here it seems like they're doing the reverse, or what they're kind of hawking at the old system of philosophy or even of theology, and saying, well, we know it's true, and now we just got to go hunt for the right theory. And once that clicks in, boy, we're just going to go out with a bang.
Right. And so he tells us the reason why they believe that it's true, or they believe that it's in the right approach, is because of the beauty and elegance of these theories, right? And clearly a beautiful theory cannot be wrong, right?
Well, I mean, E equals MC squared. That's all you need to blow up the world or go really, really fast.
Yeah, or, in that case, not beautiful. He says, we might wonder why physicists would be so enthusiastic about a theory that has no empirical confirmation as yet, right? That we can't test or anything. Well, one reason is that string theory promises to be extremely elegant and beautiful, right? And there's a good precedent for these virtues, right? That is beautiful, elegant theories. After all, Einstein developed this theory, as you mentioned, E equals MC squared, and relativity and that kind of stuff. And the reason why Einstein pressed these theories and finally, they won the day to a certain extent, is because they were so elegant and so they were so beautiful, and so they had to be right?
Sure. Why not? I mean, 10 to the 500th power, you got to start somewhere.
Yeah, that's
so
right.
Beauty and elegance sounds like just the peachy keen first step.
And so these theories that we can't test empirically seem to be so beautiful, but one physicist blames this beauty approach and elegance approach on Einstein. He says, unfortunately, Einstein himself bears a lot of responsibility for having brought about this state of affairs in the fundamental physics. He became more mystical and started to believe that mathematical beauty alone, rather than experimentation, could point scientists in the right direction, right? Regretfully, when he discovered general relativity, employing this strategy, he succeeded. And this experience spoiled him for the rest of his life, right? So it is mathematically beautiful, so it has to be right. It has to map onto nature, right? And indeed, that's what Einstein found. He worked out the math, and the math was elegant, the math was beautiful, and we found out that indeed it mapped onto nature.
Right.
And so these theories do the math, they seem elegant, they seem beautiful, so they have to be right.
Yeah,
right?
Unfortunately, that's also what we saw with Newtonian mechanics. Yes. We saw them talk about how beautiful and elegant and precise and just how great this was. In fact, Newton then even went on to continue to have that mystical understanding of the spheres and trying to prove it while uncovering for them kind of the secrets of the universe, where he was coming up with the ability to do calculus, and again you do it and it works and it's great, and you take what you learned in math class and you tie it over to physics, and the bouncing ball matches exactly what you learned in your math class, and you're like, this is amazing, this is I'm learning math now, and I'm going to say, when am I ever going to use it? Whenever I kick a ball or look at bodies in motion. This is great. And so then we just have to apply it and say, well, okay, but then there are issues with it, and then we find out it's not true, and then we have to come up with two competing theories that kind of hollow out the middle, but work great on both ends, but don't come together. They're the don't cross the streams. They just bad things come from it. You'll burn your face off.
So there is a catch though with string theory. in math. And you know what it is?
Always
He
a
says,
catch.
unfortunately, there is no mathematical formulation of string theory. Oops.
Man,
right?
I thought that was like the test.
Yeah. The story of string theory is not easy to tell because even now we do not really know what string theory is. We know a great deal about it, enough to know that it's, something really marvelous. We know, much about how to carry out certain kinds of calculations in string theory, but we do not have a good definition of it, nor do we know what its fundamental principles are.
Right.
So there's no mathematical, formulation of string theory.
Yeah.
So, oops, we kind of missed the boat here.
Yeah.
So where have we been here? Well, what we've looked at here is we looked at Newtonian. We started with Newtonian physics and said, science tells us what reality is all about. And then we found out, no, it doesn't if you use Newtonian physics, because there's more to reality than Newton was aware of and that he could explain. And so we came up with these quantum theories and relativity theories, right? And we breathe a sigh of relief. They tell us what reality is all about. Yes, but no, because now they're incompatible with one another. And so one of them either has to be wrong, something is wrong, and so we come up with string theories or M theories or whatever. But there's problems there. They're untestable. We don't have the math for them, so they don't tell us what reality is all about. So physics is a science that's supposed to tell us what reality is all about, and we still don't know what reality is all about, ultimately, with regard to these various physical theories, right? And so he says, we have decent reasons for thinking that our two best theories, general relativity and quantum mechanics, are false in important ways, and that the best candidates for replacement theory, string theory and M theory and that sort of thing, are untested and maybe untestable. So perhaps he says the future will show that the bets on string theory were well placed, but it doesn't show it now.
Yeah, but I see people going on podcasts and writing books, and they talk about how great and amazing quantum mechanics are, and general relativity, and how revolutionary Einstein was, but they're also very coached in never saying anything bad about this. And again, this is the kind of the attempt for science to kind of codify itself as the arbiter of truth. And when I say science, I of course mean scientists who have their own flaws and worldviews and objections to other people's worldviews that are attempting to kind of take the narrative and say, yes, it's hard, but look, we're really smart people, and we've done things like double slit experiment, but this is what it really means. And here's we are able to bend light, and we're able to predict a black hole just from the math, and all these things seem to work. But then when you really look at it, it's getting them certain answers, but it's not getting them the answers that they're looking at.
The whole complete picture, right? And we can. Quantum particles do not follow what we would expect them to do from general relativity theory. Right. They just don't do what general relativity says they should do, right? Yeah. And then the medium-sized and large objects don't follow quantum principles. They don't act that way, right? And so these two theories are fundamentally different from one another, and they work in their areas, but clearly there is no unification of both areas. String theory then is the attempt to do that, and again, it falls on its face, right? There's really no way to do it. Yeah. And so his conclusion is...
claims about what science has shown about God's existence. Why should we believe them if they cannot tell us about the unobservable parts of physical reality? At the same time, they don't even tell us what the non-physical parts of reality are. Right. So they can't do it with what we see, and they can't do it with what we don't see. So why should we believe them when they say, science has proven that God does not exist because, all these things.
Right.
We look at the very small and we don't see little God particles moving in, and we don't look out in the vastness of space and see the throne of heaven. And,
well, they do have the God particle.
Well, they do have, yeah. I would not. They better hope God's not there, because I'm pretty sure he has the best lawyers in the universe, and, co-opting his name. But
so if we have reason, he says, to be skeptical about what our scientific theories tell us about the unobservable parts of physical reality, right? Like, wait a minute, we're not sure what that's like. Why would we believe what they imply about non-physical reality, that God doesn't exist and that sort of thing? If you don't get it right, or if we have reason to be skeptical in this area where you're supposed to be the expert and tell us exactly, then in this other area, why would we, as good skeptics, that is, sober skeptics, why would we believe you in this other area that you don't even deal with? Right.
So that's the whole point of this chapter, is why did we learn about string theory? Because string theory, quantum mechanics, superstring theory, all the M theories, all those are, as of 2016, at the time of the writing of this book, are and have been the best attempts to answer the physicalness of the entire universe. And so when you have then scientists scoff at whether or not there's a God, well, they can't even tell you what's happening at if they're at the one end, they can't tell you what's happening at the other end, and they can kind of tell you what's happening in the middle, but then they have to refer back to a guy whose theory they supplanted with their own theory, and they just don't kind of tell you this. They're not being intellectually honest about what science actually says. So that's why we've looked at why actual science is hard, why real science is hard. We looked at the different points of having arguing with success. Well, it just seems to work. In here, it's not even working. It's, they come up with things that kind of work within itself, but you kind of have to coach it with, the mysticism, the good practices, and shaking the rabbit's foot over it and hoping that the counterspin of the other arm. We're just going to devolve back, and we're going to find out animal sacrifices does the work. So what are we to do? We're supposed to be good sober skeptics, realize what actual science is doing, and what it actually says, and what it can't do. Right, exactly. And so if it can't tell us yet physical reality truths, or workable truths even, we shouldn't take too much for stake when they say things like, God doesn't exist, or there's no objective morality, or the laws of logic exist within the universe that doesn't pertain to human existence. That's what this whole approach was, and we're coming up to the end of the chapter on science, where we're going to be talking about metaphysics and coming up with conclusions of what science might actually say about God. Right. Good. So there we have it. So we'll next time we'll look at metaphysics. Because that's, and see where we go from there. Mm-hmm. Yeah. So as always, we appreciate all the subscriptions that have been happening. Probably in a couple more episodes, we'll have a special treat for you that is interesting, that we got to take part in, and we ask that you just continue to keep liking and watching and commenting. We really appreciate it. So thank you, and we'll see you next week. See you next time.